Now, microprocessors are manufactured on the surface of a thin wafer of silicon, and I have one of them here. I hope you can see this. Each of those little squares is a single microprocessor of the kind that we saw earlier. Now, to me, it seems incredible that something which is so tiny and so complex can be made at all. It sounds almost impossible. Well, to see how it's done, we're going to have a go at doing something else which also sounds impossible. And for this, I'd like a volunteer. Should we have someone from this side? Yeah, I bet you. Would you like to come on down? Okay, just turn around. Let's come and stand here. That's good. What's your name?
Briley.
Briley. Okay. What's your initials? What are your initials?
BG.
BG. All right. I'm going to give you a big marker pen. There we go. And I have here some rice, just ordinary rice. I'm going to take a little grain of rice. And I'm wondering, do you think you could write your initials on the side of that grain of rice using that marker pen? Probably not. No, I think probably not either. Okay. Tell you what, to make it a little bit easier, we're going to do something different. Just wait there a minute. What I have here is just a sheet of plastic. What I'd like you to do is to write your initials, nice big writing, nice big fat writing, across the middle of that plastic for me. Okay? Excellent. Okay, that's good. Do you want to just go over that one more time? Make it really nice and big and fat. That's it. Lots and lots of ink is really good for this. Excellent. Wonderful. Okay, that's brilliant. Okay, let's just pop the top back on there. Now, what we're going to do with this, if you'd like to come with me, come over here. If you'd like to stand just there, we're going to take this and I'm going to pop it in this frame like this, and I'm going to switch on this light box. So this is just a box with a bright light inside. So lots of light is coming out, it's passing through your initials and spreading out in all directions. And over here we have a lens, and the lens is collecting some of that light and focusing it down onto this grain of rice. And we also have a camera which is looking at that little grain of rice as well. And if we can now take the feed, if we can take the feed from that camera and bring it up on the screen, if I keep out of the way of the light, we should just, there we can see, there are your initials written on a grain of rice. Okay? Okay, I'd like to do one more thing. Hold out your hand like this and put it in front of your initials, in front of the light box, that's it. And then hold it flat like that in front of the light box, that's it. And now just move it gently about, and we can see an image of your hand. Okay. Okay, thank you very much indeed.
A microprocessor is the brain inside a computer. It's made up of a microchip on an electronic card. Preparing the chip to be installed on the card is a delicate and precise operation. Scientists built the first computer in 1937, but it could only do algebra. The first general-purpose computer in 1946 was the size of 20 refrigerators. During the 1950s, transistors replaced bulky vacuum tubes. Then integrated circuits replaced transistors. But the biggest breakthrough came in 1971 with the microprocessor. All the components on one minuscule chip. That's what made the personal computer possible. They start with a ceramic square called a substrate. This will carry the microchip. A machine coats the substrate surface with flux, a chemical that makes it sticky. This will hold the microchip in place until it's soldered. The factory receives the microchips ready-made, with all the circuits in place. They place a microchip on each substrate. An infrared light guides the machine to place the chip in precisely the right spot. They pull a sample from the production line to further verify the positioning with a microscope. Next stop, a soldering oven at 365 degrees Celsius. The heat melts tiny beads of tin positioned on the chip, binding it to the substrate. Next, they prepare to solder an aluminum cap over each microchip. The cap will have two functions: to protect the chip and to dissipate the heat the chip generates. A robotic arm picks up 4 caps at a time and positions them over the microchips. They go into a soldering oven at 150 degrees Celsius for about an hour. The next step is to create the electrical connections that will later link the microprocessor to the computer's electronic card. They start with tiny cylindrical pieces of tin called columns. Tin conducts electricity. A giant suctioning sieve vibrates the columns until they fall through the holes. This lines them up vertically so that they can be attached to the substrate. A machine spreads a thick adhesive paste, then attaches the vertical columns in it from underneath. A robotic arm positions the chip-carrying substrate onto the pasted columns. The result is a microchip with 1,000 connections. For even more connections, they use tin balls instead of columns because balls are sturdier and more reliable. They too go through a suctioning sieve, only instead of paste, they're stuck on with flux, that sticky chemical used earlier to position the microchip onto the substrate. The finished microchip unit goes into a bath of water and solvents to remove any excess flux or other residues. Last stop, quality control testing. Up to 12 hours in an oven heated to 140 degrees Celsius. From here, the microprocessor unit goes to another factory where it's soldered onto an electronic card, which then goes into a computer. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net.
Meet the Cell broadband engine. It's the digital soul of the PlayStation 3. And though it may look like an ordinary microchip, it is the future. It all comes down to processing power. The faster you think, the more things you can think about. And that makes you smarter. Which is why the Cell has not one, but 8 synergistic processors. While a normal computer can only handle a single task at any given time, the PlayStation 3 performs multiple tasks in parallel. Everything from physics to lighting, navigation to artificial intelligence, all processed simultaneously in the blink of an eye. Take this raindrop. It has a number of unique properties, like shape, size, velocity, and weight, all of which determine exactly how it affects this pool of water. Because something as deceptively simple as a raindrop is really so complex, previous processors could only handle a light shower. Not very exciting, is it? But the Cell is 40 times more powerful than the processor of the PlayStation 2. It's faster, and it's smarter. Which means, without much effort, we can conjure up a tempest. And if we lower the temperature just enough, we discover that no 2 snowflakes need ever be alike. But with this much processing power waiting to be tapped, it doesn't take much to stir things up. As we tumble along the wind currents, we might find ourselves at the center of a vicious dogfight, as chaotic and unpredictable as the real thing. And the Cell controls it all. Not just one, but an entire fleet of enemies, each responding in real time to the environment. Every breeze, every bullet, creating a battle so furious, it'll take all your reflexes to survive. Which begs the question, with this much brain power, is the Cell broadband engine even smarter than you?